Good morning. Welcome to Expanding Energy Frontiers on Earth, Moon, and Mars, 2. Your session chairs are Lindsay Ross and me, Bill Ambrose. We hope you enjoy participating in this forum. We encourage attendees, like the presenters, to express a diverse range of professional views on energy frontiers. Before we start, let me also point out that the chat window is on the right side of your screen. You can use this space to communicate with speakers and other attendees viewing the presentations. You can also engage with speakers, attendees, and exhibitors at any time using the ACE networking portal. We would like to encourage all attendees to join the post-session Q&A discussion by clicking the Zoom link provided in the left-hand resources column on the session page. Lindsay and I have recorded back-to-back introductions for the order of speakers, and let's begin. I'll introduce our first speaker, Douglas Wyatt, whose presentation is titled Understanding the Depositional Character of Lunar Ice. Doug Wyatt is the Program Manager Director for the Laboratory and Support Services Operations, LASSO contract at the Kennedy Space Center. His team of 260 plus engineers, scientists, technicians, and specialists support research for the International Space Station, research flight hardware development and design, sustainable human flight technology, development and deployment of lunar and Martian in situ resource utilization engineering, plus basic and applied research development in materials, cryogenics, plant sciences, launch landing systems, and operational support laboratories. Doug believes that it is quite important to engage and involve the broader geoscience community in the exploration and the development of the moon. Please welcome Doug.
Hello. Thank you for this virtual opportunity to discuss a concept that we have for the depositional character of lunar ice, and I hope you enjoy this presentation. This is part of the AAPG's Energy Minerals Division Astrogeology Committee, and I'm very happy that we have such a committee in AAPG because it's very important that we use our geoscience skills to help develop the future human presence on the moon and ultimately Mars. Lunar deposition by sediment fluid interaction is just not something we've been trained to think about on the moon. We talk about ejecta blankets and solar wind impacts and scattering and even volcanic influences and some vertical tectonic influences, but it's not something we're trained to really think about, a sediment fluid interaction. But you know, now on Mars, deposition by sediment fluid interaction is commonly known. New examples are found almost every day, and the number of papers in the literature is increasing rapidly. This paper discusses the possible turbulent and instantaneous deposition of sediment fluid interactions when an icy comet impacts the lunar surface. And then the results of that are a depositional pattern that I'm going to propose and call tumultuites. The last humans on the moon were 1972, Gene Cerna and Jack Schmitt. Jack Schmitt, of course, was a geologist. But there's been continual exploration of the moon that you can read here. We have had 22 successful landers, not including the 6 Apollo missions. And although there have been some failures recently, last year, the Israeli Bereshit, the Indian Vikram lander, there are still 8 current active lunar orbiters and the current Chandrayaan rover. And we have seen physical surface samples from several places on the moon, with data from actual lunar samples from the 6 Apollo missions and the 1 Russian Lunar mission. The future is bright for lunar exploration. 24 scheduled missions in the next 4 years. I don't expect you to read this chart, but all the red dots are part of the U.S. Artemis program, and all the blue dots are various landers and orbiters that are designed to look for additional ice and water on the moon. I show a picture of the Viper rover. The Viper rover is scheduled for launch in a couple of years. I'm very proud that some of my people are working on the instrumentation for this. But we're going back to the moon, and it's going to be a very active expedition. Continuing our basic lunar geology discussion relative to deposition, there have been numerous probes since the 1990s with instrumentation for surface mapping and geological and geophysical surveying. There is much data out there. To me, thinking about the lunar surface as an igneous provenance desert regolith, ranging from very fine-grained silt to scattered rocky outcrops, helps me mentally consider my depositional thoughts when I discuss the moon, and the fact that there are no significant organic compounds on the solar exposed lunar surface due to solar wind, cosmic radiation, and temperature. But understanding that the lunar surface is full of valuable minerals, some that you see here, including some rare earth elements. All of these minerals are oxidized forms, and so there's abundant oxygen on the surface of the moon as well, plus helium as well. Geotechnically, we have some data from these sediments, and if you want to study the physical properties of the sediments and the lunar surface that we brought back from the moon, look in the lunar source book. The references here. It's wonderful information, but we have particle size distribution, particle shapes, the gravity, density, porosity, compressibility, bearing capacity, all kinds of information on these sediments, plus some interesting information that helps us think about a depositional process. Lunar sediments are typically graded as silty sand or sandy silt, and typically described as well graded. We have drilled on the moon some, not very deep, meter or two, and we have density profiles of the sediments, okay? And the density increases, and from the data we have so far becomes asymptotic at about 1.92 grams per cubic centimeter, okay? But the porosity of these sediments is very high, between 30 to 50%. People had speculated about ice on the moon since the 1960s. And this continued through the 1980s, but data was sparse earlier and generally sparse later. However, in 1996, the Clementine spacecraft detected the possible signature of ice on the surface of the moon. This really got people excited. Then the Lunar Prospector in 1998 had a neutron spectrometer experiment on board that could detect very minute amounts of water ice by looking for thermal neutrons, and it detected water over both the north and south polar region at significant percentages. What's important is this neutron spectrometer could not only look at the surface of the moon, but to a depth of about half a meter. So we were beginning to see ice on the surface and below in the subsurface. Then an experiment in 2009 later was the L-Cross and Centaur experiment, where they crashed the Centaur stage into the Cabeus crater and looked at the plume, and they detected hydroxyl at roughly 6% water and some nearly pure ice crystals. And then Chandrayaan-1 in 2009 continued to find hydroxyl signatures. People were really beginning to believe the probability and the existence of water on the moon. The 2009 discoveries of water as being a probability, of ice as being a probability, was a game changer. That means that we now have a source of material potentially for propellants, drinking water, processing water, manufacturing water, maybe even some other organics in the ice. It also added a concept to the discussion of lunar deposition, where we're not just looking for impact effects and debris scatter and moonquakes and things like that. We're now looking at potentially lunar ice freeze thaw at the ridges and edges of some of these cold traps. It's often been said that to study the moon, you need geochemistry and geophysics. That's still true, but we also need other geological concepts like the four-dimensional geologic depositional character, an understanding of that, of these ice deposits for economical, effective, and sustainable utilization. As a result of teleworking and isolation due to the COVID pandemic, I began to catch up on a lot of the literature that I had been remiss upon reading. And the image at the right is from the Lunar and Planetary Institute and the excellent work done by Stoper and Meyer and their associates. And this is the lunar South Pole. The crosshairs are in the pole, and the dark areas are craters with permanent cold traps. Cold traps exist because of the angle of the sun, the direction of the solar wind, inclination of the lunar poles, and the topography all creates areas that are permanently dark, permanently cold, with excellent potential for long-term survival and existence of lunar ice. So these areas are of great interest, particularly in the U.S. Artemis program. You see the craters Shackleton, Cabeus, Shoemaker, Amundsen, Hayworth. These are all prominent cold traps that are of great scientific interest. Right at the crosshair is the Shackleton crater. It looks smaller than the others, but it is 21 kilometers in diameter and 4.2 kilometers deep, just to give you an idea of the. Well, zooming in a little bit, using other Lunar and Planetary Institute data, you can see that the Shackleton crater is on the image on the left. You can see the Shackleton crater. You can see the crosshairs designated where the pole is. There's a box around the Shackleton crater, and the image on the right is from Zuber et al. And is a very large or higher scale look at the interior of the Shackleton crater. This fascinated me. And I actually pulled this image up and made it the background on my big screen associated with my computer. And so I could sit there and look and think about this quite often. This is elevation. So we're seeing topography on the interior of this crater. And as a geologist, every geologist seeing this video immediately starts to put patterns to what they see in this figure. So did I. And I began to think, okay, we're in a cold trap. We've got measurable satellite signature that suggests hydroxyl radicals and ice in this crater. What could these patterns actually mean? Are they just sediment? Are they sediment and ice? I had several questions to ask. So I started drawing on it just like any geologist would. You could put thousands of lines on this image to come up with various patterns. And I studied some other resources about water vaporization with comets in general. Greater than 99% of the water that's associated with a comet, the ice, is vaporized when it impacts. Almost all models show that, but not all of it is. Just for my mental research, I assumed 1% remained. And if that happens, I believe there may be an instantaneous deposition as the ice comet mass interacts with the excavated lunar regolith from the impact. And then you get immediate particle density sorting and even some geochemical interaction on large and small scales. Can this concept be tested? Is it possible to predict based on existing geological concepts? I believe so. Okay, and here's my initial concept. And I apologize to all my friends that do very advanced four-dimensional modeling. This is very simple, but it shows my ideas. You have an impact, the impact and the comet break up. You start to break up the regolith. Most of the water in the comet's volatilized away. But at some point in that process, some of that remnant ice starts to interact with that disturbed regolith. And it becomes very turbulent, instantaneously turbulent, and massively turbulent. And pulling that time 3 period over onto this slide, I believe that the result of that looks something like what you see in red here, tumultuite emplacement, in just a few minutes, if not a few seconds. Okay, and so you'd have that, like that little red figure on the bottom right, you have distributed ice, probably from fallout, but you also have tumultuously deposited ice from the impact, mixed with the sediment in various tumultuous shape forms. They can be bedded, they can be circular, they can be ball shaped, they can be various structures depending on the turbulent process at the time. And I believe these exist. I believe you can predict where they would be located. And I believe it's going to be possible to predict even what the form of these are to help you go after the ice in whatever shape or form it might be within these bed forms. And I call those tumultuites. And so I did a quick experiment. You know, I teach geology a lot online, and I had a lot of equipment with me as we were doing this teleworking, and derive some observational assumptions that I wanted to see or believe would happen, assuming some additional conditions that you can read here. And then I developed a hypothesis that a direct or glancing impact from an icy comet will create a crater, where as a result of the mechanics and process of impact, ice will interact with sediment, causing the ice to survive and form an observable and predictable depositional package. And I created an experimental concept to do this, which we'll see in the next slide or two. Picture on the right shows my experimental setup. Basically, I created a simulated lunar regolith. I did it with very fine grained sand and bentonite. And we do have lunar simulant that we use in our research programs, but it's considered a hazardous substance, and we weren't on site to get it. I wasn't on site to borrow some. So I created my own. And you can see from the grains on the center figure about the size of my lunar simulant. It was very fine grained sand to silt size, which I think. This image shows you some of the impacts as they happened. I used lead shot as a test case to see if the concept was going to work, and then I used ice ovaloids, little ice balls, as my comet. One thing we discovered was that the ice balls were much harder to aim, so I was using a slingshot as an impulse source, and you could see the velocities we obtained in the previous slide. But I had to move my impulse source closer, within half a meter, to make sure I could aim the comet I was trying to cause the impact. And this worked very well as just a very simple experiment. And you can see the results here. Okay. Most importantly, we did meet some of the scaling criteria necessary for these experiments, in that we did hit the approximate 5 or 6 to 1 diameter to depth ratio that is in the literature. Plus, we had some of the exact same geomorphic features that are found in the literature. The picture on the top with the PB is a remnant lead shot. That would be like a stony meteorite hit, and you immediately recognize that pattern. The pattern on the bottom is an icy hit, and they were almost always a little bit geomorphically different. Okay, and it was this that got me thinking about this concept of the tumultuites, and that it might have some truth there. So expanded a little bit. Here's a lead impact crater on the left and an ice ovaloid impact crater on the right, and you can immediately see, just from the image alone, that there are 3 distinct areas where the particle size has been sorted by the impact. I went to great trouble to fully homogenize this lunar simulant that I was using after every impact. So after every impact with ice ovaloids, I got this sorting pattern. Pattern varied by impact, but it was always this 1, 2, 3 pattern that looked like this. Okay, and I was thankful that the bentonite actually held the shape of the fluid transfer to my lunar simulant for just a little bit, a few minutes, and then it would eventually dry out and these shapes would fall apart. But I could photograph them. I could use my digital microscope and figure out the grain size distribution within them. But this is a depositional pattern, okay? And this depositional pattern has conditions to it. It has descriptive conditions to it. But also, if you look closely, you see this turbulent motion within these bed forms. Those are areas where the bentonite has separated itself out to form lenticular, circular, or spherical shapes based on the impact, and contain more moisture, more water than the sandy particles. So, is this tumultuous deposition? I believe it might be, and that might be a very small example of a tumultuite. So in summary, volatiles and water is the major goal on the moon. We presented a conceptual model for ice emplacement from turbulent mixing, based on a comet impact with lunar regolith. And we termed these formations, these depositional patterns, tumultuites in this presentation. And then we did a very simple experiment to see if there was any validity to it. It looks like there might be. But I would really like people to take do more advanced research into this with a more robust process and see if these tumultuites might be something that is useful for our exploitation of ice on the moon. Some of the key references I used are here. This is not exhaustive, but it's fairly comprehensive. If they're here for you to use. Thank you for this opportunity and for listening and considering. And if you would like to contact me with any questions, please do so.
I'm pleased to introduce our next speaker in William Ambrose with technical and economic restraints on resource development on the Moon, Mars, and the asteroids. Bill's affiliation is with the Bureau of Economic Geology, the University of Texas at Austin. In this presentation, Bill considers the consumable materials that can be sourced from beyond Earth and the prioritization rationales and opportunities in the context of new technologies and commercialization imperatives and pathways. Bill is a graduate of the University of Texas at Austin with his bachelor's and master's degrees in geology. Bill is a senior research scientist and focused on clastic sedimentology, stratigraphy, reservoir characterization, with additional interests in coal resources and astrogeology. Bill was president of the AAPG's Energy Mineral Division in 2006-07 and former co-chair of the AAPG Astrogeology Committee. Bill is chair of the Coal Committee for the Energy Minerals Division. Hello, Bill.
Good morning. I'm Bill Ambrose. I'll be describing some of the technical and economic challenges that await resource development on the Moon, Mars, and the asteroids. I'd like to acknowledge my co-authors, Bruce Cutright, Dieter Beike, and David Rich. Today we'll be looking at the various rewards and risks by different sectors involving exploration and development of space. First, there's the geopolitical sector. Do different countries want to compete with each other on the same place? For example, the Moon is being considered by several countries for resource development and human habitation. Or would there be more cooperative ventures or partitioning of geopolitical space? These are important things to consider because each one of these sectors contain minerals and other materials for in situ development. The private sector is becoming much more important. That includes a whole host of different activities. You can see them listed here: equipment manufacturing, example, reconnaissance operations, conducting planetary mining operations, and so forth and so on. These would involve power installations, space construction, and mining. Also, space offers a rich bounty for different types of research: geosciences, planetary surface and resource mapping, that is ongoing on the Moon, for example. Physics, space is a different environment than what we are used to on Earth, so there's an opportunity to do research in cosmic particle analysis and also the effect of microgravity, as well as the lack of Earth's magnetic field. Chemistry, there will be a lot of materials manufacturing, and of course human survivability is important in space. This is not a full array of space resources. However, it does show that on the Moon, for example, water ice is important. Water consisting of hydrogen and oxygen, hydrogen being the fuel and oxygen being the oxidizer. There's a range of potential resources according to the late Paul Spudis. This is both poles between 200 and 1,000 million metric tons. The uncertainties are because we haven't visited the poles, and these need to be proven by more focused reconnaissance. Helium-3, the total resource, if you consider all the way down to less than 10 parts per billion, on the Moon is 6.5 times 10 to the 8th kilogram. On Mars, there is an abundance of both surface and near-surface water ice. It's in excess of 5 million cubic kilometers, of which about 1.2 million cubic kilometers is in the northern water ice cap. And the asteroids, a typical asteroid that's metals rich, 1 kilometer diameter, would host about 1.74 times 10 to the 5 metric tons of the precious metals, including platinum. And then other strategic metals and minerals, copper, cobalt, titanium, chromium, nickel, and molybdenum, not quite 9 million metric tons. And this does not even include the volatiles resource, which includes water ice, ammonia, and various carbonaceous compounds, and helium-3, which all could be used for human habitability and rocket fuels. Private investment is becoming increasingly more important in space exploration. In 2019 alone, the commercial market was $400 billion, of which $300 billion was tied up in communications. Morgan Stanley estimates that by the year 2040, the commercial market will balloon to about $1 trillion. The catalyst has been in the form of the price that Dennis Tito was willing to pay to fly to the International Space Station in 2001. So there's a tourism impetus, which will be augmented increasingly by a commercial impetus consisting of mining, processing, and supporting human habitability in space. You can see that private investment is considerable, more than $25 billion amongst 535 unique space companies since 2009. And last year alone, almost $6 billion. NASA has fostered a relationship between industry and the government. And you can see that from 2005 to 2013, there was an emphasis on a program called Commercial Orbital Transportation Services. The NASA program budget was $800 million, leveraged with private partners. In 2008, there was a shift from being partner to a consumer via commercial resupply services contract. This involved non-human rated missions to the International Space Station for supply, followed by human rated missions, of which we've recently seen an example. And you can see that alone the contracts for different companies like SpaceX and Orbital Services Corporation in 2008 were $1.6 billion and $1.9 billion respectively. That has been increasing. In 2009, there was already a substantial increase. And by 2014, it is believed that a tipping point was reached where private companies are now providing at least 25% of the funding for a variety of selected projects. In situ sustainability development is the important pathway for maintaining a human presence in space. In situ mining of materials for construction and propellants and various manufactured products would be manifested in the form of planetary industrial parks, housing and living environments, and manufactured goods. As an example, some of the activities that have already been undertaken by private industry. Bigelow Aerospace has been working on habitation modules. They successfully deployed one at the International Space Station recently. Lockheed is developing the Orion-based lunar lander to return humans to the moon. SpaceX launch vehicles for both the moon and Mars. Odyssey Moon, robotic lander and rover. Honeybee Robotics will be involved in drilling and improving ice resources, extracting ice cores at the moon, at the poles, and cislunar space development transportation systems consisting of tugs and shuttles. There are a variety of limitations and risks, however, in planetary mining operations, and these are business considerations that have to be considered. Compared to Earth resources, for example, the costs are going to be substantially higher in form of CapEx, which are capital expenditures, OpEx, operational expenditures, G&A, general and administrative expenditures. The resources will necessarily have to command very high prices to be competitive. The main risks, and there are several of them, this is the second group of text. The completion risk, contractual arrangements may not be achievable. The markets will have to endure unusual locations, for example, permanently shadowed regions at the lunar poles and also near-Earth asteroids. Also, we're involving microgravity environments and very low temperature environments where machinery will have to operate in areas that are just a few degrees above absolute zero. The bottom bar limitations, essentially there will be competitiveness for materials on planet Earth, and obviously it will be cheaper to mine certain commodities on Earth for a very long time. And we would want to do that. Deep sea minerals, for example, polymetallic sulfide ores and nodules, ferromanganese crusts. We could go to Antarctica and Greenland. However, these may be sensitive areas, and so it might be a reasonable alternative to go to the moon for some of these materials or to the asteroids. Essentially, the delta V situation is what drives costs of transporting materials from the Earth to the moon. Delta V is essentially the change in velocity required to go from one component of the Earth-Moon system to the other. So to get out of Earth's gravity well, just a low Earth orbit, or LEO, is about 8 kilometers per second. From LEO to the moon is a little bit less, 6.3 kilometers per second. LEO is the site, for example, of the International Space Station. GEO is geosynchronous orbit, where we have numerous communication satellites. L1 and L2 are Lagrangian points, which have somewhat stable gravitational environments where any material that's placed in L1 and L2 would be relatively stable, and it wouldn't take much energy to maintain, say, for example, a space station at L1 or L2. The resource costs, the lifting costs, just simply increase as you go from the Earth to the moon. And that's not a surprise because it involves more changes in delta V to get from the Earth to the moon. And that's what's shown in the blue bar in the bottom graph. So, for example, to manufacture water, for example, on the Earth is negligible. That's the tiny blue line that you see on the far left part of the graph. But as you go higher and higher, getting away from Earth's gravity well, the cost to transport materials from the Earth to the moon becomes increasingly higher. So that, for example, it would be about $35,000 per kilogram to take water from the Earth to the moon. Obviously, the cost of manufacturing that on the moon has to be considered, but you would not have to transport that to the moon if you could manufacture water on the moon, and that's what the yellow bar or the yellow tower is indicating. Looking at lunar helium-3 distribution, it's very asymmetric on the moon. It's the result of helium-3 being bound up in titanium-rich, more mafic basalts, which are quite common in the lunar mare. There are numerous examples of them on the lunar near side, which is on the left side of the diagram. On the lunar far side, which is dominated by a north acidic crust, there are very few examples of lunar basalts, and consequently very few places where helium-3 is in abundance. Helium-3 would be a source for nuclear power from fusion. And you can see that the concentrations are low, rarely exceeding more than 50 parts per billion, but ore containing 20 parts per billion could be strip mined and could be heated up to very high temperatures and extracted from the lunar regolith or the soil. Polar ice, both the North Pole and the South Pole, is where we would want to go to extract the lunar ice. These are areas within permanent shadows, otherwise known as PSRs. And we're looking down on the North Pole. On the left side of the diagram, we're looking down on the South Lunar Pole on the right side of the diagram. And you can see that the different colors on, for example, the North Pole, these are areas where we have fairly good evidence for concentration of lunar ice from a variety of probes. The green dot on the right, the series of dots are from the Moon Mineralogy Mapper in cubed, LOLA, which is the Lunar Orbiter Laser Altimeter. diviner, which measures thermal inertia of materials. Then in the blue, we have all of these probes, which were carried up by the Lunar Reconnaissance Orbiter in 2009, and also Chandrayaan, augmented by another sensor called LAMP, which is the Lyman Alpha Mapping Project, which is an indication of hydrogen. Let's look at Mars and see what the Earth, the resources are on Mars. It's the most Earth-like planet in the solar system. It's the second closest planet. A conventional rocket of chemical propulsion would take more than 200 days just for humans to get there. It could be achieved in far less time in an ion rocket, about 40 days. Earth-like seasons in the day are quite comparable to that of Earth. Also, if you take all of the land surface of Mars, it is equal to the land surface of the Earth, because Mars has, even though it's smaller, a 44,220 mile diameter, it's composed of all land, and therefore that adds up to a very considerable land area. There's quite a very large concentration of water resources on Mars. You can see here, this is from the Mars Odyssey. The purple, which is at the top of the diagram, which is more than 64% concentration of global water, is in the form of the polar ice cap. The dark blue areas that are adjacent to both the North Pole and the South Pole are high concentrations of Martian permafrost. And interestingly enough, in the equatorial regions of Mars, there are areas of some concentration of water, at least 16% in the form of what we call tropical mountain glaciers, which are mobile collections of basically near-surface glaciers that are in the state of flowing from high areas to low areas. I'll show you examples of those. If you compare the Earth and Mars in terms of the ice caps, we're looking at the Antarctic ice cap on the left versus the Martian ice cap on the right. It's composed almost entirely of water ice. Mars has a polar cap on the south, but that's composed almost all of frozen carbon dioxide. You can see the thicknesses and the volumes are different. However, it's still considerable on Mars. Mars has a maximum thickness of 3 kilometers of ice at its northern cap. In Antarctica, it's about 4.5 kilometers. The volumes, however, are much greater on the Earth and Sea. In terms of glacial ice, I mentioned what we call tropical mountain glaciers, and these are areas in the shallow Martian subsurface that are ice-rich and which are slowly flowing due to gravity. And you can see that in some cases. Here's an example from Holt, 2008, in a Science article that documents that the subsurface ice glacier is 730 meters thick. That's comparable to an Earth glacier on the left, which is entering the Bellingshausen Sea. And note the very large scale of these Martian glaciers. The city of Austin, for example, which is about 30 kilometers across, is tiny compared to the outline of these very smooth areas, which are corresponding to Martian glacial ice. Near-Earth asteroids also feature a variety of resources. These are local sources for in-space rocket fuels, volatiles, oxygen to support space missions, but they also contain an enormous supply of platinum group metals, a variety of other metals, cobalt and nickel, and also REEs for rare earth elements for strategic minerals. Asteroids and comets also provide windows into the early solar system, so they're a valuable commodity in terms of research. And also they're a great concern for human survivability on the Earth, because there's many Earth-crossing asteroids that potentially impact the Earth. In terms of their composition, most of them are the C-type, carbonaceous chondrites. The S-type, which are the stony asteroids, are about 15% of all asteroids. And the M-type, or the metallic types, are the ones that would contain the metals. just a very small M-type asteroid, 3554 Amen, contains a huge amount of materials. It has a mass estimated of 30 billion tons, a considerable market value of iron and nickel of 8,000 billion or $8 trillion, cobalt and platinum group $6 billion each. And you can see that these are considerable assets. The problem is how to get them from space down to Earth. And also, if we wanted to access these and start producing these in large abundance, then I think we have to be concerned perhaps of glutting the market and decreasing the value of these materials because they would be so abundant. So in summary, there is a global market already developing in space. Last year it was $400 billion. It may be by the year 2040, $1 trillion. There's a whole variety of potential activities for technology development, communication, remote sensing, propellant and materials transfer. All of these would be for power systems, human habitability systems, and manufacturing systems. Limitations and risks are considerable. There's a limited potential for Earth supply, for example. The markets have to be created. There's a high equity risk. And of course, there's also a high risk to control the costs and also scheduling and performance of projects. And thank you for your attention. I'm pleased to introduce our next speaker for the session, Matthew Brzostowski. His title presentation is Milankovic Cycles on Mars and the Impact of Economic Exploration. Dr. Matthew Brzostowski has over 40 years of energy industry experience, specializing in seismic exploration. He is a graduate of Washington State University with a degree in geology, University of Texas at Dallas with a doctorate in geosciences. Matt has supported NASA's DRATS work at Meteor Crater and helped archive, reprocess, and interpret the Apollo active seismic data. An active member of the AAPG Astrogeology Committee, he believes in the relevance of applying Earth analogs and processes to the Moon and the planets. Successes in understanding the Earth's geologic evolution to Mars is the basis for his presentation today on Milankovic cycles. A Fourier analysis of the Earth's and Mars' orbital elements will be presented and shown how they can be used to guide future exploration. Welcome, Matt.
Today I'd like to talk about Milankovic cycles, both of an overview of Milankovic cycles on Earth and how the evidence for Milankovic cycles influencing climate, especially ice ages, and then talk about how Milankovic cycles could be used to predict what's occurring on Mars in terms of deposition or water cycles, and how it can be used to exploit economic exploration, especially for minerals such as hematite and gypsum, and how it could be used to maybe explain other features on Mars. Just a quick overview of Milankovic cycles. This is straight from Wikipedia. The key curve here to start off with is Milankovic's curve here in the middle here, the black curve. It shows the insolation or the solar radiation that impinges upon a latitude of 65 degrees north. I'll explain a little bit more why that's used in the curve. But essentially it's the energy variation over time as a function of the orbital changes with the Earth going around the Sun. So these orbital changes include obliquity or the tilt, top curve here in blue. It also includes eccentricity or how unlike a circle the orbit will be, and this changes quite a bit over time as well. And then we'll also look at the longitude of perihelion, which is how the orbit precesses around the Sun. The two key parameters that go into Milankovic's equation will be obliquity and then the precession index, which is a combination of eccentricity and the longitude of perihelion. Eyeballing this real closely though, you can see a time scale on the bottom, up to 800,000 years in the past on the left here. If you look, you can kind of see within the tick marks of 100,000 years, you can see 2.5 cycles here, probably like a 40,000 year cycle associated with obliquity. We'll confirm that later with Fourier analysis. You also see about 100,000 year cycle associated with eccentricity, and we'll confirm that later for analysis as well. But what you do see is that eccentricity has a strong character on top of the precession index, and you can see almost like a beat nature when you combine eccentricity with the perihelion. Now, on top, besides the astronomical parameters and elements and how they are combined for the Milankovic cycle, we also have some supporting evidence. I'll cover these in greater detail, but for this particular curve, there is supporting evidence associated with the delta oxygen 18 isotope for foraminifera in the deep ocean cores, the benthic foraminiferas. And what we'll see is that there's a very characteristic sawtooth curve associated with the oxygen 18 isotopes. The oxygen 18 will vary as a function of temperature. And what you see on the bottom is a Vostok ice core curve. The core is over here on the left. And we'll see later how that is determined. And but the primary thing for this graph is that you see a cyclical nature as well, corresponding to the benthic forams. And it's almost a 100,000 year cycle here. You can see the eyeball. There's more periodicity in here than that, but you can see that as the temperature drops, according to the Vostok ice core, the oxygen 18 isotope goes up. And we're going to link those back to the Milankovic cycles later on. We're going to do a Fourier analysis of the Vostok curves and compare that to the parameters associated with the Earth. And then later we'll use the Fourier analysis for Mars as well. Start off the equation, just a busy slide, but just a couple of high points. The key equation down below is basically the change in insolation over time, or the change in radiation. Two key components of that will be the obliquity factor, or the tilt, and then also on the right, the precession index, which is a combination of the centricity and the perihelion. What's quite interesting is that the obliquity, or E, is this curve down here. In green, we're using eccentricity, which is that part of the equation down here. And in the long-term perihelion, we're going to use a summer half here. And what's quite interesting is that Milankovic, as well as Bruckner and Kopnin, said, well, the great number of cold summers must be the cause of glaciation, which I thought was quite interesting, not necessarily the cold winters, but colder summers. And so that is going to be entered into the right side over here underneath the yellow portion. We were going to use 65 degrees, that's going to be phi, which will go into here, cosine phi, as our latitude. Now the elements that go in here, Milankovic used Pilgrim's astronomical elements, as well as Stockwell. More modern day, you can use Quinn. I'm actually going to use Armstrong's work that he used for his PhD thesis associated with wind erosion on Mars. These are curves that Milankovic published. Most of his work was done pre and post, pre and part of World War I. And what you see here is the curve going from 0 modern day times to 300,000 years, and then continuing on the bottom up to 600,000 years. He computed the insolation at 65 degrees north, but what he computed here is that said, well, if the insolation is less, then it'll appear like 65 degrees north. It will appear almost like the same insolation as something higher, in this particular case, about 70, 71, 72 degrees. While if the insolation is higher, or more energy coming to the 65 degrees north, that latitude will appear like it's actually lower in latitude, about 60 degrees. So roughly view this as warmer and colder. But the most interesting thing he did is that by looking at some of the work by Pink and Bruckner, and in particular by Koppen and Wegener, Wegener is the same Wegener that talked about plate tectonics. He noticed that the lower portions of temperature, insolation, temperature, seem to correspond with glacial moraines, glacial terraces associated with some of the alpine streams or rivers. These rivers are called the Wurm, the Ries, the Mendel, and the Goons. And in fact, people studying classical geology would remember these as alpine glacial periods. And it was a rough correspondence in the early days associated with the Wisconsin, the Nebraska, and Kansas glacial periods in North America. But the primary thing here is that Milankovic said, well, it looks like insolation curves do correspond to global cooling or global warming, which is what these curves represent. There's additional evidence, though. As I said, the Vostok ice core, the analysis of this core, this is on the Vostok Russian base in Antarctica, very deep core. There's a very thick ice cap in the Antarctica, and plotting left to right, modern day up to 450,000 years, you see here plotted a time and temperature. Now the time and temperature are derived from the analysis of the core. One, you can count layers over time, just like you do count tree rings. You also can count, you can do an analysis of the air bubbles that are trapped and the density, and you can do analysis of the air bubbles. You can look for oxygen 18 variations versus the norm, or even the hydrogen isotope variation versus the norm. If there's carbon matter, you can do carbon 14 dating of that carbon. You can also look for volcanic ash associated with known volcanic eruptions. And you can also measure the boreal temperature to get an idea of the actual temperature. So that's the basis for coming up with a temperature scale and a time scale for the ice core. Our interest, though, is to take these elements and do a Fourier analysis, look for periodicity, which is what I've done on the right here. You see a few peaks here, a strong peak at about 0.01, and that corresponds to a 100,000 year cycle, which I mentioned earlier in the graphs before. But you also see a couple more peaks, 40,000 about, and 28,000 year cycles. We'll see how those relate to Milankovic cycles a little bit later. Just the explanation about the oxygen 18 isotopes changing. When it's colder, it's a little bit easier to evaporate the lighter isotopes for oxygen. Those end up being in glacial ice, so these would be deficient in oxygen 18. While in the deep ocean sediments, especially the ones with the foraminifera, the foraminifera should have a little bit higher oxygen 18 content. That's the basis for looking at oxygen 18 and the change in oxygen 18 versus the norm. Say a normal time here for before and after glacial periods. So the foraminifera, this work was done in the 70s by Shackleton and Opdyke, and what they did is they plotted the oxygen isotope ratios over as a function of depth, and what they were able to do is come up with 19 stages, and they were able to relate those or calibrate those to a rough time scale, 700,000 years for stage 19, by looking at the magnetic polarity reversal, so the Bruins and Matsuyama. So this calibrated the stages, and so the stages become a very definitive aging technique. In fact, if you look at the spec map, that's the marine isotope stages that's used for dating deep sea sediments. Likewise, this can be applied to other ocean cores. This was done by Hazenbury and Shackleton in the 70s, looking at the Indian Ocean cores, and it is statistical analysis, and we're able to find a few peaks of periodicity, 100,000 years, which we've mentioned before, 40,000 years, and a couple others at 24 and 19. What's interesting at the time is that they found that Vernecker looked at the tilt cycle and corresponded to be 41,000 years, and precession cycles of 23 and 19,000 years, which comes very close to matching what they're seeing in the Indian Ocean cores. Masalula and Kukla also looked at reef terraces and were able to correspond to different ages as well. They saw cycles of 100, 41, 23, and 90, similar to what we see here for the ocean core. So reef terraces should as well have a geomorphological input associated with astronomical forcing with climate change. And here's a plot of that from Embry's book, Reefs in Papua New Guinea. And in fact, similar analysis was done for the Barbados, but you see 100,000 year terrace here as well. And of course, in the oil and gas industry, we're pretty familiar with sea level fluctuations, especially the Vail curve, a more modern update by Halam. But associated with, now this is over a longer time scale here, but you see marine transgression regression over time. And in fact, the high stand here would be back in the Cretaceous, which we know the epicenter oceans in the mid-continent North America was inundated with the high stand here. Also can be applied to cyclostratigraphy, a work by Wheaton and others. This is actually belemnite marls, and he did an analysis of these belemnite marls, and he came up with bedding, decimeter scale bedding, and they seem to relate, if you do a statistical analysis, it seems to relate to the 20,000 year orbital precession cycle, the cycle we mentioned earlier. And this is actually his analysis of the three cycles that you see associated with precession, about 24, about 22, and about 19. So once again, you can use analysis, statistical Fourier analysis, to come up with cycle periods and see if those relate to deposition, in this case belemnites, associated with stratigraphy. So now I went ahead and did a Fourier analysis of the Earth's elements. I took the precession index and I did an analysis and came up with 3 peaks. These peaks correspond to 24, 22, and 19, just like we saw earlier. So just reaffirmation of what I showed earlier in the other graphs by other people. And likewise, I did the analysis of Earth's obliquity and a very strong peak at 40,000 years. So just a reaffirmation that the Fourier analysis that I'm going to show for Mars is reaffirmed and confirmed with the analysis I did for Earth and corresponds to the geomorphological evidence we've seen so far. So we have a good foundation to extend what you know about Milankovic to Mars, I would say. So just to review Earth's orbital cycles, the tilt, about 42,000 years. This comes from Hayes, Embry, and Shackleton, the original publication in 76. Precession periods of 26 say and 23 years, and an orbital eccentricity of about 100,000 years. I did not show the eccentricity. I showed the combination of the precession index, but it corresponds quite nicely. All right, so then I took Mars elements for obliquity, the change in obliquity over time, and I went and did a Fourier analysis. And I came up with one very strong peak at 128,000 years cycle. So that's one data point to work with. I didn't do the eccentricity, but I did the precession index, which is more common today. And once again, looking at the element over here on the left and the Fourier analysis on the right, very strong cycle at 73,000 years. So 128 and 73,000 year cycles is what we're predicting for Milankovic cycles on Mars. So Milankovic and Head did an analysis similar, looking at the Mars polar caps, the north cap here, and what you see on the right is a picture of that cap, and then the square here is a zoom, and that white line there is another zoom, and you see a lot of layers in a cap, which is not surprising. And they predicted a obliquity period of 120,000 years, which is real close to what I have in the Fourier analysis of 128, but they have a precession and eccentricity periods of 51 and 95. Now mine was a precession index, a combination of the two, which I came up with 75, so maybe it's the average of the two there. But that's the point, is you can start looking at Milankovic cycles, and maybe we can take a ice core of the polar cap and look for these cycles within the ice core and try to understand how much astronomical forcing are influencing the climate of Mars. Likewise, we can use the Milankovic cycles to look for ore exploration. This is a nice picture of the Homesick Vein Endeavour crater, the Mars exploration rover. It found a gypsum vein, very narrow but distinguishable gypsum vein. And the interesting thing about gypsum is that it is associated with water deposition. You see the H2O associated with that. And so maybe we can use the Milankovic cycles to come up with a hydrological cycle to understand the deposition of some of these gypsum deposits. Likewise, the famous Martian blueberries, the hematite, they are also associated with water deposition. And once again, maybe we can do some cyclical stratigraphy analysis to understand what cycles may be associated here and what cycles are associated with Milankovic cycles on Mars. Finally, if there is life, and these are just two possibilities, no definitive definition of life yet on Mars, but the more interesting one is this bacteria on the right. This is it's called a polyextremophile. Extremophile, and it can live in some very extreme environments, thrive in extreme environments, high radiation, ultraviolet or desiccation, oxidizing. So, if anything, this is a possibility for Mars. The interesting thing about the radiation, it can withstand up to 5,000 grays. Now, for comparison, the Apollo mission, 1 milligray, 5 grays will kill a human. 2 to 800 will kill bacteria E. coli. It'll take 4,000 to kill a tardigrade. This is a tardigrade down here. So now tardigrade is not actually an extremophile because it actually adapts, and adapts quite well. It can do almost down to absolute zero temperature by releasing water. But these are possibilities. The point of putting this slide here together is that maybe there is a cyclical nature associated with the growth of life associated with Milankovic cycles. So in conclusion, shown with Fourier analysis that Mars obliquity cycle is 128,000 years, while the precession index cycle is 73,000 years. So we can use these to predict and affirm deposition on Mars, I would say. We can use these to look at ice strata, maybe ice cores, to look at isotope variations and see if this relates back to Milankovic cycles on Mars. We can look and see if there's cyclical bacteria colonies associated with this water cycle or climate change cycles. We can also use it to try to predict ore deposition and mapping and prospecting, sort of like what Vail has done to help us with oil and gas exploration. And with that, I'd like to thank the audience for attending today.
I'm pleased to introduce our final speaker for this session in Titus Murray with hydrologic models of faults in unconventional coal seam gas and mining projects. Titus's affiliation is with Southern Highlands Structural Geology, based in Bowral, New South Wales, Australia. Titus today presents conceptual groundwater models in the context of coal seam gas developments and fault seal analysis, and considers 3 cases modelled for flow-through with variable aquifer and aquitard relationships. Titus is a graduate of Flinders University in South Australia with degrees in geology, geophysics and computing. Titus is a structural geologist with extensive experience in the study and characterisation of faulted and fractured reservoirs in over 30 countries. Welcome, Titus.
Hi, I'm Titus Murray from Southern Highlands Structural Geology. This is some work that I've done with Bill Power from Power Geoscience. He's based in Perth in Western Australia. And we're looking at how to conceptualise faults for groundwater in and around coal seam gas developments. Here in Australia, we've had a lot of coal seam gas developments over the last 10 years. There's been a significant discussion about the impact of coal seam gas, in particular surface groundwater assets for stock and domestic use, and for groundwater dependent ecosystems. So the federal government here has put together a bunch of guidelines and a bunch of ideas and come up with a concept of causal pathways. Now it's a bit of word salad here, so we're just going to go through and just clarify. As structural geologists, we can tell you that there's a connection between a fault and an asset. We then start to invoke, well, could that be a potential flow pathway? What would be the characteristics to make it a flow pathway? A causal pathway is a logical chain of events that link a coal development and have a potential impact on water-dependent assets. Now, to do that, we need to understand the flow modelling. So a potential pathway then becomes a causal pathway if we go and do the groundwater flow model. It may be that it draws down a bore by 30 centimetres. We then need to then it needs to be considered what happens at that stage. That 30 centimetre drawdown may or may not be important to a groundwater dependent ecosystem, and so that groundwater flow model then needs to be taken on by ecologists. There are a whole range of ways that we conceptualise faults. We think of faults as being leaking features. We can leak across them, we can leak up them, we can think of them as being barriers. And in the oil and gas industry, we commonly think about faults as being barriers to flow. And that's how we generate traps. In other areas such as mining and tunneling, we're concerned about water flowing down into the subsurface. There tends to be a bias from where we're coming from. So there's the good, the bad, and the ugly of fault science. And the really important thing with any fault science is you have to demonstrate it's a fault. We need to have demonstrable displacement along the length of a fault. The fault analysis group did a fantastic set of work with British Coal, and this great paper is about a bunch of collieries in Yorkshire where they went through and mapped in detail the displacement along faults. So we need to show that we have a maximum displacement on the system that diminishes out towards the tips. We need to show that it has a sensible length throw ratio, and we need to make sure it's got sensible dips. Where we start to get into the bad, I'd say, is when we're starting to think about faults and saying they have a characteristic. Uniformly, this fault has a thick core and a wide damage zone. As you'll see, and as we've seen from looking at faults in the field a lot, that faults aren't systematic in this fashion. The other thing is they're not systematic in terms of lithology. You can't sit there and say, oh, because I'm in a limestone, I'm going to get this sort of fault. And look, where I think it gets really ugly is that we are invoking faults as being features which have no demonstrable displacement. I'm suggesting that they're very wide. yeah, a lot of the data we have a look at on faults, these faults are relatively narrow. The work of the Fault Analysis Group has shown that, and the work that Sylvia de Rosa done in MIRI is systematically looking at the variation in fault thickness at 1 meter spacing along the strike of the fault. That yes, the fault will be thick in some places, but if I move 2 meters to the left or right, it becomes very thin. And this concept of a fault core, which is in the order of 1 meter thick, doesn't hold up. Fault rock tends to be thin. So when we have a look at faults in the field, we've got ourselves layers in the footwall, we've got layers in the hangwall down thrown over the fault surface, and that the geologist's view. We can then start to think about, well, what potential hydrogeologic features would we have in this system? We can start to catalogue that. Well, look, we've got ourselves fractures. These are bed-bounded fractures. We've got ourselves aquitards, and we've got aquifers, and we might have fault rock. If we put that together as a static conceptual flow model, then we'd start to say, well, look, my yellow zones are areas of matrix flow, the red are where I'm going to see strike parallel fracture flow, and the green are where I'm going to have no flow. So effectively, I can't flow into the aquitard, but I can flow across this area of reduced permeability across this little window, whereas this window down here is much bigger, and so it's going to have a larger area of and that geometry as well as the flow features is vitally important. This is the area that in MIRI that Sylvia and I worked on, and yeah, it looks like a fantastic wide fault zone, 60 meter throw fault, textbook. But when you start to think about this and you start to think about the anatomy of these things, you've got a damage zone, which may be 5-10 meters thick. You've got yourself a slip surface and a fault core. Now, if you think about this in terms of the overall scale of the fault, we can start to use length throw ratios, and we can start to use, the Fault Analysis Group has done a really good job of these displacement thickness cumulative frequency plots. So if I have myself a 50 meter throw fault, that will generate me something like a 20 meter wide damage zone. And if I'm really, really going for it, I might have a 50 centimeter thick fault core. And Sylvia's stuff and the stuff we saw in this outcrop in MIRI, it's more like 10 centimeter fault core. Now, the length of that feature is going to be somewhere between 2.5 kilometers and 5 kilometers. Now, if you take the ratio of the length to the fault core thickness, that gets us a ratio of about 0.02. To put that in context, if I take my telephone bill here, this is an A4 piece of paper, it's 300 millimeters in length this way, and its thickness is 0.05 millimeters. And that gives me the same ratio. So that is as three-dimensional as this fault in MIRI is. And you wouldn't think of that as a 3D object. It really is a 2D object. And what's important about it is how things are juxtaposed across it and how it enhances flow in that damage zone parallel to it. In our main bit of practice in the oil and gas industry, what we've seen is that we can show that none of the membrane seal mechanisms work in the data sets we've looked at, and that we get a much better result predicting fluid contacts if we assume that fault rocks don't exist over geologic trapping timescales. So we're saying, well, look, faults are going to tend to leak across areas where we've got sand on sand or aquifer and aquifer juxtaposition. So these are the things I need to do a fault analysis when I'm considering hydrogeology. The first thing I need is geometry. I need the geometry of the fault. I can't just sit there and say I've got a fault. I need to show how long it is, how much displacement's on that fault. One of the great methods that's out there just now that's becoming more common, and Geoscience Australia done an amazing job of collecting huge data sets of airborne electromagnetics. This stuff sees it's under a helicopter, it can be flown over long line lengths, and it sees down to about 200 meters and gives a really good understanding of that near surface aquifers. Ken Laurie at Geoscience Australia did a fantastic job of showing how near tectonics and faulting can come through. If we're talking to people, we need to show decent cross sections. We need to show what the geology is. We can't just sit there and say, oh, well, in the Permian there weren't any faults. We actually need to illustrate that, and it needs to be done as balanced and sensible geologic cross-sections. Dick Glenn at New South Wales Geologic Survey made these beautiful cross-sections, pencil and paper, in the 1980s through the the Hunter coalfields, and they're beautiful, consistent, geologically consistent models. It's easy to go and use. I use Lithotek to make this, to forward model these same sorts of similar geometries, and it's easier in Lithotek, but you can do this with pencil and paper. Having got a sense of the geology, we need to understand where the aquitards are. And as with normal oil and gas fault seal analysis, I'd sit there and say understanding your seals, where your seals are, is your primary concern. And putting that in context of a sequence stratigraphic framework is really important. How good is that seal system or that aquitard? And describe it as thickness maps and as distributions. So to help us understand how to think about coal seam gas developments and these near-surface assets, we've put together a set of scenarios. The first scenario is, hey, my faults are irrelevant. I don't need the structural geologist to help me. And the way I can show that is, I can show that there are no faults in the region. You're completely flat lying. Or I can say, I've got a regional aquitard that is nice and thick and none of my faults juxtaposed across that. And my aquitard is a ductile material that won't prop fractures open. So what I need then is I need a set of fault statistics to illustrate the scale of my faulting and catalog those faults. And I need a good ISOPAC of the aquitards. So to give an example, this is from the Santos Narrabri environmental impact statement. I haven't personally worked on this. This is stuff in the public domain. So what Santos are proposing is to develop a set of coal seams in Narrabri in here. And sitting on top of it are a set of aquifers that are important to the Namoi River and a set of aquifers related to the Great Artesian Basin. Information from the Geologic Survey, and I can see I've got a Narrabri shale, which is a mean 141 meters thick. Santos have done a good job of giving us an understanding of what our aquitards are. So they're calling Narrabri and the Digby as an aquitard. So that's these units in here. And so I've got myself 173 meters of aquitard with standard deviation of 45 meters. They've got a depth structure contour map. Unfortunately, it's of the Maules Creek down low in the system. Ideally, I'd be wanting to see a depth structure contour map base of the aquitard. But nonetheless, I can see with my 40-meter contours, I might be getting in the order of 80 meters displacement on some of these faults. And so I can use a length throw ratio to sit there and say, none of these faults are going to have enough displacement to juxtapose the 173 meters of in there. And so then if I start to look at my assets, the blue assets are the river asset, the yellow is irrigation, and the green are park assets. And so we can start to say, well, look, none of these faults are anywhere near those. This is the development area in here. This is the development area in here. The maximum thickness of everything sitting in here. So we can start to put together a conceptual model saying, no, these faults actually aren't important. So that's scenario one. Scenario two is I don't have regional aquitard. I've just got a stack of aquifer, raw aquifer or coal seam, and as I draw it down, what's going to happen is I change the pressure in there. My pressure response is going to be preferentially travel parallel to the fault and the fault damage zone. So this is the damage zone in the fault in Miri that Sylvia and Zoe Chipton did a fantastic job of cataloging and describing. And my flow is going to be in and out of the page parallel to that fault zone. This is again a project I haven't worked on, a group called Senex in Queensland, where they're looking at the Walloon coal measures as coal seam gas development. The developments in the red squares in here. They've got themselves a nice geologic section which shows the Walloon coal measures is dark grey colour. They've got a really good outcrop map that shows where this is. And the issue we've got here is we've got obvious faults sitting in here. We've got the coal measures at surface. There's no aquitard between them and any near surface assets. Now their assets are actually further away. They're well outside the lease boundary, but we can start to say, well, what effect would the faults have in this? If we have a look at the coal, this is the coal measures. You can see that it's pretty finely bedded. It's not a fantastic coal resource at all for mining, but it does have a lot of gas in it. And what we can see in there is, well, we're not going to propagate lots of fractures because of the mechanical stratigraphy. They're going to be very much bed bounded, and they're not going to be going through the whole system. So that means that features like this in here are going to have fracture transmissivity along strike. what we need to do for this fault in here, as you can see, we've got changes in strike. We need to go and look for the displacement along there. Is that a lateral relay ramp? Can we show and demonstrate that these systems aren't connected through changes in displacement? Produced a table of aquitard and aquifer thicknesses, minimum, most likely, and mean. We just need to do a proper study on this one to understand the displacement along that fault. The final scenario, which becomes a little bit harder, but it's not that bad, is we have multiple aquifers. And this is the third scenario where we've got unconfined aquifer at the surface and one or more semi-confined aquifers down before the coal measures. If our fault displaces that, it takes us away from scenario one, then we're going to need to generate Allen maps. It can be used to illustrate the connectivity across the whole system. In summary, so what I really want, I want geometry. I want to understand the geometry of the system. I need to have decent cross sections that explain and describe the geology to everyone. I need to have a good characterization of my aquitard. Have I got myself a decent set of maps which have throws easily measured, so then I can generate fault statistics out of them. It's important to have tick marks and contours you can count, and then where needed, illustrate the displacement and juxtaposition across the system using Allen maps. I hope that helps, and we'll look forward to questions afterwards.